The next assignment you're going to have will be assigned on Monday, and then it'll be due on Friday of next week. It's going to include some problems related to softening, which is what we're covering today. And then next week we'll begin discussing ion exchange and reverse osmosis. So, the interesting thing about each one of these topics that we may only spend a single class period on, or even half a class period in the case of ion exchange and reverse osmosis, is, you could spend an entire 3-year PhD studying some small sub-aspect of that topic. So we're just really scratching the surface, and the main point of this approach is for you to get the familiarity that would enable you to go to a water treatment plant and kind of understand the things that people are talking about, and so that you'd know what resources are available to learn more about the design processes. And so we will do certain things this semester in a fairly good level of detail where you're doing genuine design and where you're sizing things that could be built in the field. But then on a lot of these smaller subtopics, there still is elements of design that we simply don't have the time to cover. And unfortunately, softening is one of those that we have to speed through, but there's a lot there. For our first midterm exam, that's going to be on Monday the 26th. So that's, I guess, about 9 days away, 10 days away. It's going to cover lectures 1 through 14, and if you want to see the corresponding textbook material and the topics that go to those classes, it's available on the schedule of topics that's the last page of the syllabus on Blackboard. It will include some problem solving and concept questions, and I haven't yet written the exam, so I'm not sure precisely from a point standpoint how many, like what fraction of your grade will come from concept questions versus problem solving, but you'll need to be able to do both for the exam. As far as preparing for that, you can bring in a page of notes and you can put anything on that page that you like, whether it be definitions of terms, formulas, previously solved examples, just anything that can help you to remember and remind yourself and feel confident going into that exam that you'd be able to solve any of the examples that we've worked together in class or any of the homework problems that you've submitted, and that you understand the concepts that are discussed in the book. So because we're skimming through things, just using softening as an example, there's a lot of chemical reactions in our chapter on softening that I don't expect you to be able to regurgitate those chemical reactions, but there are some concepts that we're talking about today and some supporting material related to those concepts in the book that I would ask you to know well enough that you could describe and explain things on the test. So I think if you've had exams with me before, you probably have an idea of what this next one will be like, and if you haven't, then you'll know really soon. All right. So today we're going through Chapter 7. Before we begin on that, are there any questions on the announcements? All right. So hardness. There are these kind of seemingly non-scientific terms that are used to describe certain parts of water treatment and wastewater treatment. And hardness is one of them that is as much a historical term as a current term. From a technical standpoint, like if we're being quantitative about it, the way that you calculate hardness is by adding up all of the polyvalent cations. And so anything that has a charge of greater than 1 is a polyvalent cation. So that could be calcium, magnesium, iron, manganese, and those are the 4 constituents that are found in the largest quantities in water. And so they're the ones that would contribute greatest to hardness, but even things that should be in really low concentration that are polyvalent, like arsenic or chromium, those would technically be contributing to hardness as well. As we often do, instead of leaving it at their individual ionic concentrations, we try to standardize and combine the effect of different ion constituents by expressing it in terms of milligrams as calcium carbonate. So it's just kind of a standard unit of measure, so that one water which has a lot of magnesium and a different water in a different town which has a lot of calcium, you could compare and understand the impact that they have on the thing that people observe with hardness. And so what people actually observe is the effect, and it's called hardness because of the feeling on the skin when you're using hard water. And it's most noticeable if you've ever bathed at a place that's using reverse osmosis or ion exchange. Some people who have money to burn, I guess, they use rock salt in ion exchange systems to replace the calcium and magnesium in the water with sodium ions. And so you strip out the calcium and magnesium and you replace it with sodium, and so therefore the overall charge of the water hasn't been adjusted, but sodium doesn't contribute to hardness. And so if you shower at some place that's using that ion exchange softening, that ion exchange will take the hardness all the way to 0. And so the water feels just excessively slippery, and it almost feels like you can't rinse off the soap. Now, the flip side of that is hard water. The water almost feels rough on your skin. And it's not that the water is rough, it's just that the soap and detergents that you're using, they can form a precipitate, which that's what you're feeling on your skin, is kind of the abrasive effect of that soap not being in solution. So soap scum or poor lathering is observed, and showers that kind of have like a white residue on them. I mean, you're wondering, ew, is this like bacterial or something? It kind of looks like a disgusting fungus, who knows? But I mean, it's really just calcium precipitating with the soap particles. And nowadays, most people don't actually even use soap. They're using synthetic detergents that are in a bar. So soap is the combination of lye and fats. And so sometimes you'll use real soap if you go to like a farmer's market and you're buying it from somebody who's made it themselves. But if you go to the store and you're buying a bar of Dial or whatever, it's usually detergents rather than a classic soap that's made out of a basic substance combined with fats. But hardness still can reduce the effectiveness of cleaning, and it can also cause scaling of pipes. And this is a really interesting cross-sectional view of a pipe that has its flow area dramatically reduced compared to the water that should be able to flow through that pipe, just because there have been a number of years that calcium and magnesium have been depositing due to excessive hardness. So I guess either one of those could be thought of as hard. Mineral deposits on your skin or mineral deposits on the pipe. It's all about minerals. And so if we think about where hardness comes from, the water that's in the atmosphere doesn't have polyvalent cations in it. Like if you think about a puddle that evaporates and it's up in the sky and we have these droplets of clouds that falls down through the atmosphere, there's no ions in rainwater, but the rainwater hits the ground surface and it's going down through topsoil. And there are bacteria that live in the vadose zone. The vadose zone is that region of soil that has both some moisture and some air. And so there's bacteria living in there that generate CO2. And you probably remember from chemistry that when you have water and CO2 is mixed into it, that forms carbonic acid. And so that's lowering the pH of the water. Now, on its own, at a neutral pH, calcite and dolomite don't dissolve much at a pH of 7. They're not very soluble. But at a depressed pH that can be formed from even just a little bit of carbonic acid, then there is a shift in the distribution of calcium and magnesium species, and it forms species that are soluble in water. And so calcium bicarbonate, magnesium bicarbonate, they do dissolve in water. So basically, the acidic water that is permeating down through a limestone bed begins to absorb the characteristics of the minerals in that limestone. Hardness also comes from other things besides calcite and dolomite. If these other chemicals are just less common, so things like concentrated deposits of gypsum or magnesium sulfate, magnesium chloride, these are all potential contributors to hardness as well, just not as geographically abundant. Any questions so far? Okay. So if we think about what have we got here in West Virginia, we have relatively hard water. I've got a slide here in a moment that maybe shows the political boundaries a little bit easier. But where they really suffer from hard water is in the Intermountain West, Utah, Colorado, western Kansas. And the thing is in these western locations where they have less surface water, hardness is kind of a double whammy because they don't have access to already available surface water, so they're more likely to use underground water resources in these locations that there's a lot of dissolved magnesium and calcium. So it's really a problem in these regions in red. You can see that Ohio and some of the Appalachian region also has elevated hardness. And so here's a table that classifies hardnesses as calcium carbonate. So remember that regardless of the constituent species that's contributing to hardness, just to put it all on an easy level playing field where we can compare place to place, it's expressed as calcium carbonate. So what we usually wouldn't notice, would just feel pretty normal, is a hardness between 100 and 150. That would feel pleasant to people. It wouldn't cause problems with detergents and soaps, and it wouldn't cause really quick and problematic precipitation in pipes. Now here's another figure that also illustrates it, but it's showing the concentrations, rather than in terms of milligrams per liter, it's grains per gallon, which is just kind of an old-timey way, with units that are in the traditional system of grains. The other place I guess you maybe hear about grains occasionally is with bullet reloading. People talk about grains of powder. And so a grain is 64.8 milligrams. And so 1 grain per gallon is equivalent to 17.2 milligrams per liter as calcium carbonate. So if we look here in the tri-state area, we're in the hard water but not the very hard water range. Where they've got very hard water would be up in Columbus, central Ohio has very hard water. But luckily they have a lot of surface water that isn't often as hard as the groundwater. So who's most affected by hard water is people who live outside of the city limits and maybe they're just on a well at their home. So some of those people, I guess earlier I said that ion exchange is for people who've got money to burn. I guess it's also for people who live off the city water and just have such hard water that they've got to do something about it. So it is a real issue. Now, let's go through an example here just to get some practice calculating hardness. And if you have a computer, then this is one that I think lends itself nicely to being solved on Excel. So this is the result of an analysis that we could get from a lab. And we've got a representation of some cations and some anions. Does anybody know how you'd take a water sample and figure out which cations are in there? There's a couple of different ways. One of them that I used when I was doing some experimentation in graduate school is something called an inductively coupled plasma. And basically you take a noble gas like helium and you heat it up super high so that it turns from a gas into a plasma. And a plasma is kind of a fourth state of mass. You know, there are solids, liquids, and gases, but then there's also plasma, which is a fourth phase. And so when you have a really hot plasma, then you could inject a water sample into it, and then these different cations will emit light at a different wavelength. And so you've got a camera looking at the plasma, and then if you're putting in water with calcium, then you'd see a little blip in the light that's being produced at a certain wavelength. And you'd know how much calcium there is by the relative intensity of the brightness of that light compared to a standard. Like maybe you'd inject a known 100 milligrams per liter of calcium into the plasma, you'd see how bright the light was, and then you'd inject an unknown sample, and then you could scale the intensity of the light that's coming off, and from that infer how much of each of these cations are present. So, you know, inductively coupled plasmas, one way to measure cations. Another one, which is kind of related, is called AA, which I think stands for atomic absorbency or something. ICP is the more modern method. And then for anions, there are things that are called liquid chromatographs, where you take a water sample and you'd inject it through a tube that has specialty chemicals that are absorbed to the outside of the tube, I guess the inside of the tube. So you're putting a solution through this really long tube, and the different anions will absorb to the chemical coating on that tube for a certain period of time, and then they come out at different times. And so maybe chloride would only stay inside of that tube for 3 minutes, whereas sulfate would stay inside of that tube for 7 minutes. And so it's a way to differentiate between different anions, and then you could quantify them as they come out. So let's just say that we took a sample of water and we got this report. The report would say the concentration of that species, and then I've already provided the molecular weight for each one of these, either cations or anions. And then remember, the molecular weight of calcium carbonate is 100.086 grams per mole. So I suggested that this would be a good one for us to solve with Excel. Let me just fire up Excel, and we'll take a look at this together. Okay. So we'll start with the ion. Let me make this a bit bigger. And if you don't have your computer today, that's all right, no problem. So we've got calcium 2+, we've got magnesium 2+, iron 3+, sodium HCO3, it's bicarbonate, sulfate SO4 2-, and chloride. I won't bother doing the superscripts and subscripts. Our molecular weight for each one of them in terms of grams per mole is that the calcium is 40.078, the magnesium is 24.305, the iron is 55.845, the sodium 22.99, the bicarbonate is 61.0158, sulfate 48.0305, and chloride 35.453. Okay. So far we're just transcribing what was already given, so no calculations yet. You know, up at the top I'm going to have the equivalent weight of calcium carbonate. And we've talked about equivalent weights before. Does anybody remember what that is? how equivalent weight is different from the molecular weight?
The molecular weight divided by the charge.
Good. Molecular weight divided by charge. So if the molecular weight of calcium carbonate is 100.086, if calcium carbonate is in solution and is dissolving into its constituent anions and cations, it's going to have a calcium +2 charge and a carbonate -2 charge. So for us to find the equivalent weight of calcium carbonate, it is the, what was it, 100.086 divided by 2. So this is our equivalent weight in terms of grams per mole. All right. So the reason why I bring it up is we're going to calculate for each one of these ions what's the equivalent weight of the ion. So equivalent, I'll just call it EW, equivalent weight in terms of grams per mole. Okay, so for the calcium, our equivalent weight will be the molecular weight divided by what? What's the charge? It's 2, so we divide by 2. Okay, same thing for the magnesium. It's the molecular weight divided by 2, because that's the charge. The iron, though, has a charge of 3+, so I'll do this iron divided by 3 to get the equivalent weight. The sodium is 1, so it's the same. The molecular weight and the equivalent weight's the same. Now the HCO3- has a single charge, so it is that. It's not a charge of 3-, it's 3 oxygens, and the anion as a whole has a -1 charge. Sulfate is a -2 charge, so it's going to be this 48 divided by 2, and chloride is a 1 charge. So now we've got the equivalent weight for each one of them as this intermediate column. And then the other given data that we already had was the concentration as the ion species. It's not yet converted to as calcium carbonate. It's just the concentration of the ion. And so it was 99, 8.3, 1.8, 15, 255, 49, and 37. Those were our concentrations. Okay. Let's create a column that is the ratio, the equivalent weight of calcium carbonate to the equivalent weight of ion. So this is going to tell us the multiplier we use to convert from the concentration to as CaCO3. So the equivalent weight of calcium carbonate is 50, and I'm going to anchor the reference there because as I drag this down through each successive row, I always want it to look up here at this location to use in the numerator of the ratio. Okay, so that divided by the equivalent weight of the ion. It's going to tell me that for every gram of calcium that I've got, it's basically 2.5 grams of calcium carbonate equivalent. So this ratio is what we'll use to calculate the final column, which is going to be milligrams per liter of, as CaCO3. So it's kind of like just our unit of measure is standardized to a species that we understand well, calcium carbonate. Okay, so it's the concentration multiplied by the ratio. Okay, so we've converted in these spreadsheet calculations, we've converted from the concentration that was measured experimentally to this standardized unit of combining dissimilar species as CaCO3. Let me turn on some borders here just to help guide the eye. All right. So we were wanting to know here, overall, what's the total hardness? Okay, so the total hardness is, remember, the sum of the polyvalent cations. So we're going to add together the calcium, the magnesium, and the iron, because they all have a charge of greater than 1. But we're not going to include the sodium, because sodium just has a single charge. We're also not going to include the concentration of any anions. Only the polyvalent cations go into the hardness. Okay, so our hardness is 286 milligrams per liter as CaCO3. That's our hardness. How much of that hardness is associated with the carbonate anion? We call that carbonate hardness. Just to make space here, I'm going to make this column a little bit wider. So carbonate hardness is going to be equal to the as CaCO3 of our bicarbonate. So it is 209.1 is the carbonate hardness, milligrams per liter as CaCO3. And then the non-carbonate hardness is the difference between the two, between the total hardness and the carbonate. And the reason why we differentiate between carbonate hardness and non-carbonate hardness is because of what it takes to get the different kinds of hardness out. If we want to remove carbonate hardness, we only have to add one chemical. But if we want to remove non-carbonate hardness, we have to add 2 chemicals. So that's why we keep track. Okay? So 286 milligrams per liter. Where does that put us into the comfort zone? That's in the hard range. We're approaching very hard. So probably this would be a candidate that would need water treatment. So then the question would be, are we going to have to, will we be okay with just that single chemical, which would remove the carbonate hardness, or do we need to go all the way and also take out the non-carbonate hardness? And if we took out the carbonate but left the non-carbonate hardness in, then that would put us in the very soft range. So it'd be okay. So we probably wouldn't need to bother removing the non-carbonate hardness from this water to make people happy. And in fact, as we'll talk about in a few minutes, we wouldn't even need to remove all of the carbonate hardness. There is a way to do like a partial removal. Even though in a chemical reaction, when you take the pH to the zone where the calcium begins to precipitate, it's kind of an all or nothing proposition, but we get around that with a little bit of engineering trickery. Any questions so far on the example? Okay. Now, lime soda softening, it's not actually like lime soda. It's just those are the chemicals that are, those are the common street name for the chemicals that are used. And so lime is more expansively called hydrated lime. And calcium hydroxide is what actually does the reaction. But calcium hydroxide would have to come to a treatment plant as a liquid. And so it's just cheaper to, instead of that, deliver the precursor to hydrated lime. And so through a process called slaking, if you bring powdered calcium oxide and mix it with water, then it will generate the hydrated lime. The thing is it's very exothermic. Our book says it's about 1 megajoule per mole. And so it's the kind of reaction that has the potential to be explosive or to boil water. And so it's kind of a dangerous part of the treatment process. Remember, we've talked before about how disinfection can be risky because we've got all this compressed chlorine gas. Well, the slaking process is another one where people tread lightly and make measurements carefully because it's just giving off so much energy. So what we want is hydrated lime, and that will remove carbonate hardness. And if we need to further reduce the hardness, but there's no more carbonate left, then soda, which is more expansively called soda ash, is what's added to provide the carbonate that could draw out the rest of the hardness after all the carbonate is used up. So we'll talk about the different phases and steps of the chemical reaction, but these are the two primary chemicals. Now there are other things that can be used besides lime to increase the pH, but that's why we're using lime. Why this chemical in particular? Because what we're doing is the opposite of what that bacteria in the soil did. The bacteria in the soil generated CO2 and lowered the pH, made the water more acidic. And when the water was acidic, then calcium and magnesium dissolved in the water. So the opposite of that is, instead of dissolving an acid into the water, we're going to add a base. We're going to take that water and increase the pH to where those dissolved metals begin to precipitate out. So hydrated lime is just one chemical that you could use, a caustic agent, to raise the pH. It's the most cost effective. There are other ones, other chemicals that maybe will generate less sludge, but they can cost between 4 to 6 times as much as hydrated lime. So people usually will go with the less expensive chemical and just deal with the fact that it generates a fair amount of sludge. Okay, so lime softening is where we're adding first of all, slaking the powdered lime, turning it into hydrated lime, and then the addition of that hydrated lime to water raises the pH, and the chemical reaction begins at a pH lower than 10.3, but if we get it to 10.3, then the precipitation reaction is much more rapid. You'll begin to see the precipitation of calcium out of water maybe as early as a pH in the mid-8s, like 8.5, the precipitation will begin. But if you add a little bit more lime, you get a lot of bang for your buck, because the precipitation occurs more quickly, and that means that the contact basin doesn't need to be as large, and the settling basins can be smaller as well. So remember, we're doing this to take the pH from the acidic range up into the basic range. And so in addition to precipitating out calcium, it's also removing any carbonic acid that may still be existing in the water. Sometimes, if you've got a lot of carbonic acid in water, they may aerate the water to try and strip it out and save a little bit on the lime that's used. So from place to place, you may sometimes see an aeration step before softening, and where that's the case, it's because they're trying to economize on the amount of chemical that's used by stripping out the carbon dioxide prior to the lime softening step. So aeration wouldn't actually remove any hardness, it just removes some of the chemicals that are in water that are going to interfere with the lime before it can begin to remove hardness. Okay, so that's lime softening. You'll hear the phrase excess lime softening referring to the chemical step of we're trying to remove magnesium. So it's just adding even more lime because the magnesium is a little bit more persistent. Its equilibrium reaction into a solid occurs at a higher pH than does calcium carbonate. And so getting the magnesium out requires that you take the pH up into the range of 11. And of course, it'll also begin earlier than that, but just to achieve time-efficient precipitation, you need to take the pH to the range of 11.3. And then the final, I guess, layer of sophistication is when you're trying to remove the non-carbonate hardness, you have to add soda in addition to lime. So there's two different things. There's two primary constituents that are contributing to hardness, calcium and magnesium. Like if we look at the quantitative effect that the iron had, it was just minuscule. And this is a really high concentration of iron. Like iron typically would be less than 1 milligram per liter. So here we're saying even if it's double the typical concentration, it still has a minuscule effect on hardness. So calcium and magnesium are the main things that we worry about when it comes to softening. And so there's two different chemicals that are primary contributors to hardness, and then remember the difference between hardness, which is carbonate, and hardness, which is non-carbonate. Softening also offers the benefit of removing other things that are dissolved in water besides calcium and magnesium. You know, they're not the only things that we'd like to get out of the water. And so when we go through this process of raising the pH, other things precipitate as well. Other things that we're glad to have out, like arsenic, barium, cadmium, chromium. All of these are carcinogens that are just wonderful to have removed. And the raising the pH gives you a pretty effective removal, sometimes in excess of 95% removal of these problematic constituents. And so there are benefits to the removal of natural organic material, which is a disinfection byproduct, which can be a precursor to disinfection byproducts. So you've got this precipitation that kind of sweeps other things out of solution as well. So this is just kind of a side benefit to softening. Because of the cost associated with really large contact basins, treatment plants are always looking for ways to save space and allow themselves to cram more treatment into less land area. And so there are solid upflow contact basins like this, where it's an integrated rapid mix and sludge settling basin, where you can see that the water would come in through the center here and would be mixed in this mixing zone with the chemical, the hydrated lime, and then the pH is changed in the center chamber, and then the water is going out under a skirt, and the water flows up at the same time that the sludge and precipitation stuff is settling down, and then is scraped off the bottom of the circular clarifier with kind of a squeegee system that shovels it all into a hopper, and the sludge is taken off and dewatered. So this solid upflow contact basin is a way to just combine two things into the same place. You're combined, well, I guess maybe three. Rapid mix, the precipitation reaction, and settling is all happening in the same tank. And then the water, once it gets to the top, it flows over the edge of a weir. Here it's called a launder. That's just another name for kind of a long trough that the water is flowing at a low velocity over the weir so that it doesn't disturb the settling of the flock down beneath. So remember that this whole removal of hardness was accomplished by us raising the pH. And we can't leave it high. You know, people aren't going to like it if the water coming out of the tap is caustic. Having a pH in the 11 range is just, it's too much. It could cause corrosion. It interferes with the disinfection process. And so the abnormally high pH that we caused when we added all this lime, we have to bring it back down again. And that's accomplished through recarbonation. And it's just exactly what it sounds like. They take compressed CO2 In the same way that they make Pepsi, they put CO2 into the drinking water to bring the pH down again. So they'll bring it in on big trucks or even rail cars, CO2, and treat the drinking water with that. So adding CO2 brings the pH back into the normal range. And another reason why we do it, besides the fact that it would interfere with disinfection and that it caused problems in the pipes or in people's use of the water, is that we have to recarbonate. Otherwise, the precipitation reaction will kind of just keep going. Like there's always going to be a little bit more hardness in the water, and given enough time, it'll continue to precipitate. So we don't want the calcium carbonate continuing to precipitate in other treatment steps that are after this softening step. So if I'm just showing you a diagram here, one of the things I mentioned that we could do with some engineering trickery is to not take the hardness all the way down to 0. But precipitation, from an economical standpoint, it's if you take the pH up to 11, you might as well precipitate out as much of the hardness as you can. And so what they'll do to economize is they'll have only a portion of the flow that they soften, and they'll bypass some of it, and then they'll mix together the softened water that has a 0 hardness with the original hardness water, and they'll blend it until they get somewhere in the middle, some target hardness that people are happy to have, and then it just means that you didn't have to use lime on all of the flow that's coming through. You just use this blended approach to get to the hardness that people will live with.
But then does that other bypass water, does that not benefit from the contamination?
That's right.
As well?
Yeah, you don't get the benefits of the arsenic removal, the chromium removal, lead. Yeah. So you only get the benefits to that portion that is in the first stage stream that is getting softened. Yeah. So it's a balancing act. Hopefully your source water doesn't have a ton of chromium and lead and mercury to begin with. If it did, then maybe they wouldn't do the bypass. They'd say, well, we'll just bite the bullet here and use up more lime because we really need that heavy metals removal. But places that didn't have a lot of heavy metals to begin with in their source water are happy to blend because it just saves lots of money. You don't have to recarbonate as much, and you don't use as much lime in the first place. So this is just an example of a split flow treatment that would enable you to get a blend. So from a chemical perspective, once you take the pH up to 11, all of the hardness that's there, you might as well remove it. But we don't have to get the hardness to 0 to make people happy. So that's why we do the blending, for economics. Okay. There is a very brief video that we'll watch the first part of as a summary. Or should we watch it on high speed? Because it's 7 minutes long and we've got 4 minutes. So if I played it at double speed...
Sandwich your head.